Like we did yesterday, these types of problems are called work rates. You can identify them because it has to do with any type of problem where you have objects doing something and some mention about how long it takes the two of them separate and how long it takes the two of them together. You can accomplish these problems in any number of ways, and I want to start with this one because this is about as complicated as some of the early problems get. Read it first. Crane Alpha can unload the container ship in 10 hours. Crane Beta can unload it in 14 hours. Stop. I had a couple of questions come in about how to address word problems if they have been difficult for you. And the first thing I've mentioned is step by step, and just take each sentence and translate it into something you know. So, alpha, we'll start with that. What we know about alpha is that the 10 hours defines its work rate. Alpha works one ship, 10 hours. That's its rate. When you do a rate, time always goes in the denominator. Just if you think about traveling in miles per hour or meters per second, this is going to be a rate, ships per hour, which is the same thing as saying 1/10 ship per hour. That's how fast it can do this. Beta, then, we can do the same thing. One ship, 14 hours, or 1/14 ship per hour. So that's how fast it can do it. Next, we have how long it actually works. Crane Alpha started to unload the ship at 12. Crane Beta started to unload the ship 2 hours later. At what time was the unloading job completed? What we can kind of ascertain here is really what we are looking for. We're looking for how long, meaning number of hours. Make that a better H. We're looking for how long Crane Alpha worked. Crane Alpha is the one that started earlier. Technically, if we know how long either of them worked, we'd be fine to answer the question of when the job was done. But we need to know, we're looking for how long Crane Alpha worked. So we're going to do a let statement. Let T equal number of hours Crane Alpha worked. Can you then tell me how many hours Crane Beta worked? Wait, his hand. Let's go with that. Chase, you're technically first. Why minus?
Because they worked 2 less hours.
Technically 2 fewer hours if we're going to go with old grammar here. But, yes. If Crane Beta starts 2 hours later, it's slacking. It's working fewer hours. Does that make sense to you? Sometimes the later people will be tempted with the plus, so just be careful that you have that relationship correct. It's working 2 fewer hours. Now, we know that they're stopping at the same time because they're both stopping when the job is completed. That should make sense. So think about Crane Alpha starting and you're hitting a buzzer. You're hitting a timer. Actually, sorry, 2019, you wouldn't do a timer like that. You'd probably say, Alexa, start a clock, stopwatch. But still, you're starting a timer, and that timer is going to end when the job is done. 2 hours later, Crane Beta starts coming in and making the job go quicker. Even though it's a slower one, it's still putting forth some effort. It's contributing to the whole thing. So we have a couple of pieces here. We have the 2 rates, and we have the 2 times. Can we combine this now and do a rate times a time for each of them? Without doing a table, I'm just going to do a rate. In fact, I'm going to dissect this a little bit more. In 1 hour, Crane Alpha does 1/10 of the job. we'll say of the ship to be specific. Crane Alpha does not work for 1 hour. How long does it work for?
2 hours.
2 hours. So if in 1 hour it does 1/10, then in T hours it does not 10/10. 10/10 would be 10 hours. 1 hour to 1/10, 10 hours to T over 10. That's the variable part, T/10 of the ship. Or T times 1/10. So that piece becomes T over 10. Let's do the same piece for Crane Beta. How long does Crane Beta work?
1 hour.
T minus 2. And if I take that and I plug it in, T minus 2 times 1/14 is T minus 2 over 14. T over 10 represents the fraction of the job that the first one completes. T minus 2 over 14 represents the fraction of the job that the second one completes. The two fractions added together should equal one complete fraction of a job, which we just define as one ship. Each of the other pieces was a fraction of a ship, how much of the ship is unloaded. The two of them need to add together. We need to figure out what T makes that equal 1. So they've completed one complete job between the two of them. Okay, now we're just down to LCD and we're down to like solving with other methods. So the setup is going to be the tricky thing here. And the more you do this, the better you're going to get at it. What's the LCD between 10 and 14? You could do 140, but you're probably doubling too big. 70. If you kind of want a quick way to do LCDs, and some of you probably already do this, to multiply them together, but then try dividing by 2 and just seeing if that works. It can be like a little quick trick to get this going, but 70 will work. It's the most efficient one to use. We're going to multiply the left and the right side both by the 70. So when I multiply the left side and right side, right, both sides, we get 70 times that would be 7t. 70 into 14 into 70 is 5, so 5t minus 10 equals 70, or 2t is equal to 80, or sorry, 12t is equal to 80. Oh, it's glitching on me, but not on you. 12t is equal to 80. T is equal to 80 twelfths. Let's play the simplification game. 20 thirds. 6 2/3. 6 hours and 40 minutes. And then let's go back and actually answer the question. T was defined as the number of hours Crane Alpha worked. Crane Alpha started at 12, so it finishes at Henry would say?
1840.
Yeah. Admit it. You want the clocks in the school to be a 24-hour clock.
They were for like one day.
Not retweet.
They were? That's so much fun.
Why don't we do those? I don't want to have your
Too much addition.
Is it too much addition or is it too much subtraction on our part to go the other way and to make it? You know why the day is into two 12-hour increments? Because clocks couldn't do 24 numbers around. Okay. Ooh, old problem. I didn't even change my name on it. Although technically this is an older scenario, so at the time I would have been Coach Elliott, which matters. Okay. This is a true story. I thought I'd create a scenario, and it's like we craft too many things. And this is not like I'm sitting actually calculating this, but I do have to run a quick thing of like, can we actually do this? So this is a realistic scenario. It used to be that the sectional was on a Tuesday and the regional was on a Saturday, same week. They changed that for obvious reasons. That was ridiculous that they did that. They ended up doing that one year because the state meet fell on the same day as an IU golf tournament, and IU couldn't host the state finals, so they backed everything up a week, but the schedule was already set, so they had to back regional up to the same week as the sectional, so they put sectional on a Tuesday. And if you know anything about running and distance running, having a meet on a Tuesday, like a championship meet, and then doubling back and running another one 3.5 days later is just massive hell on anybody that does that. It's injury prone, it's all that. You need recovery time. We're even insane right now for doing 4 levels of that 4 weeks in a row. Like they go county, sectional, regional, semi-state, state, 5 weeks in a row of championship, like fast as you can go racing. It's not good on the body. But in any case, what would happen is we'd have to, and if you've ever seen our cross-country course, we have to stripe the course on both sides for most of its journey when it's not in the woods, which is a significant part of it. So this involves somebody usually taking the striper, and between the 2 stripers we have one that has a giant paint thing, and you can just go forever, and it's battery-powered, and the other one is done by air cans, and you just put like 12 to 15 of these things in, and I'm like rolling one while I'm shaking the other can so that when it runs out you can just swap them and then grab another one and shake them. I prefer the latter because I know how to use it well. The first one runs out of battery or runs out of paint and you're in the middle of nowhere, and then you have to go and like shake the other big paint thing and run all the way back. It sucks. But in any case, this job takes a lot of time. I've gotten it down to be faster than this. Like I know the route to go to do it well, but it's still like an effort. So since we have the sectional meet, or sorry, the county meet, which we have to have it lined for, usually we let the lines go to sectionals. Like we let we used to host the county, the sectional, and the regional, and I try to line it really well so we could hold it for all 3. But inevitably we'd always have to like touch it up for the regional. Well, what happened one day is that it looked really good for the sectional. We were going to keep it for the regional. Like it's Friday night, I'm like checking it out. I'm like, okay, this is fine. They can see where they're supposed to go. And we just kind of ended practice early, went to a team dinner, came back the next day, and Jim Hughes, who works on the grounds, had mowed everything down, and just the lines were gone. It's the morning of the regional meet. So it's 7 o'clock. I'm at school. The first race is at 8:30, and there are no lines indicating where anyone's supposed to go on the course. And I don't like honest to God, at the time I probably can do it in about 90 minutes now, but it would take me about 2 hours back then. Coach Kinnear he's a little older, he's a boomer, he gets a little distracted from time to time. There are other coaches in the area, and he talks to other people, like who's constant. So it takes him about 210 minutes, which if you do the math is longer than 2 hours by a lot. But he has offered to help. Okay. So I had to grab and say, this is our only mission right now. Everything else is secondary. We have to get this done. Can we finish in time for the 8:30 start? If I can do it in 2 hours and he's going to contribute, but it takes him that long. So let's do this. We are also starting at the same time and we're ending at the same time. And we're trying to ascertain if the time that we have is less than 90 minutes. So here we go. My work rate is 1 course in 2 hours. Kinnear's is 1 course in how many hours? And I'm going to now make this be 1/2 course per hour. And I'm doing that because it's important to kind of pull that out. Even though it's the same number, I'm pulling out the units down, and I'm making the units be courses per hour. And then Kinnear's, I'm simplifying this down a little bit. Instead of saying 1 for 3.5, what's the whole number ratio? 2/7. Good. This is 2/7 courses per hour. And then like before, we're going to let T equal the number of hours we work. Unlike before, this is a little easier because we're starting and stopping at the same time. We're both working the same number of hours. So my 1/2 courses per hour times number of hours plus Kinnear's 2/7 courses per hour times the number of hours equals to 1 course. Freshmen, you're not very adept with dimensional analysis. Sophomores, you're going to be spending a lot of time with dimensional analysis, but dimensional analysis means this. If I have 1/2 courses per hour and I multiply that by the number of hours, the number of hours cancels and I'm left with courses. So really what I have here is part of course, which I should write not with thick writing. Let's rephrase this. the 1/2 t is the part of the course that I do plus another part of the course equals the one whole course. The units match. And that becomes extremely, extremely important for those of you in chem that you're going to be doing a lot with dimensional analysis to try to make your units work. Units will become more important than formulas. Okay, let's simplify this down. T over 2 plus 2t over 7 equals 1. I'm just writing that in a format that helps us kind of trigger the part of your brain that goes to LCD, which would be what? 14, not the world's worst LCD. So 7t plus 4t equals 1. Kidding. There's a thing that happens when 1 is on the right side of the equal sign that somehow makes, like a subtle part of your brain sometimes forgets to multiply by the LCD. You may have noticed this in your work from time to time, and I will see this at different points. It should be 14. Okay. Now, we get 11t is equal to 14, and t is equal to 14/11, which is 1 and 3/11. 1 and 3/11 is less than 1 and 5.5/11. And I wrote 5.5/11 because what is 5.5/11? A half. So you can do the there, or we finish with, we could kind of work this out. So if we finish with 2.5/11 hours to spare, 2.5/11 hours is 5/22 of an hour. You can scale that up if you want to and see what we have, but it gives us basically just enough time to make it to the team prayer and pretend like nothing happened. Woohoo, hashtag be brave. Huh? No. I was just overthinking it. I just spilled coffee on my glasses. Like, but it takes a special person. And like kick back up and like definitely hit that. Okay, next. Speaking of chemistry, you do, and we're going to do them from a very, very algebra style. But I told a couple of you guys that I have taught chemistry here for several years, and I would always challenge myself with whenever we would do, or whatever, I would have to make up a lab and make solutions for everyone. I would do it using not the stock ones that are already in the back, but they have like overflow ones from previous years that are marked as to what concentrations they are. So I always like try to recycle stuff that's already been used rather than like always go into the stock and use the source and create more and more clutter. So it was a challenge. It required math, which, no biggie on that one. But this says how many liters of water must be added to 20 liters of a 24% acid solution to make a solution that is 8% acid. Okay, when you see a solution problem, this can actually be really, really, really easy on you if you just set up well. I'm going to recommend tables on this because it's actually going to be a nice way to organize your information and to kind of put little check marks off of like that you have everything. So here's what you have: 24% acid. Ouchie, that would hurt. What are you adding to that? Water. Agua. And then underneath the agua, you're going to make an 8% acid solution. There's a word for this. Yes. This is a dilution. So, make no mistake, 8% acid is still going to hurt like hell. You'd have to really, really get down to like 0.0000 something percent before you like stop feeling it. But no, let's just not. But I did have a college chemistry professor who was so like trusting in his chemistry that he would do something like where he would take a solution of hydrochloric acid, which is extremely toxic, and he'd take that and mix it with a solution of sodium hydroxide, which is extremely basic. And if you know your reactions, HCl plus NaOH mixes to form NaCl, which is table salt, and H2O, which is water. it completely neutralizes itself out. So what he would do is he would take and show us the acid burning something, show us the base burning something. He'd take the precise quantities, mix them. You let it sit for a minute, then he'd shake it, then he'd chug it.
Oh.
Oh.
What if he messed up one day?
If he messed up, then the one or the other would burn his esophagus, causing internal bleeding, and he'd die out. Okay, here we go. We're going to do kind of a rate time distance here thing, but our rate is not a rate. It's not so much as it's a percent. Percent acid is acting as a rate. A percent is the amount of acid over the amount of solution, so it does act as a rate. Time is not a time, since it's percent acid over percent, or amount of acid over amount of solution. This is the amount of solution. And that's going to be in liters. And then the final one is the amount of acid, which is also going to be in liters. So if I take the percent acid and multiply it by the amount of solution, I should get the amount of acid that's present. That should make sense to you. You want to set these tables up so that the first two columns multiplied gives you the third column. So this can be tricky, but it should make sense. We're going to add it to 20 liters. That's okay. We got 20 right there. 24% acid solution is 0.24. I know that 8% acid is 0.08. Be careful with that. Not 80, but 8. I don't know how much water I'm adding, so that's going to be unknown. So now I'm going to do the logical steps. I'm going to do this in a different color. Everything I just put in now we get from the problem. But now what I'm going to do is start to fill in pieces, two pieces specifically. This piece and this piece we can think about. Let's start with this piece right here. If I take 20 liters of acid and add X liters of water, how many do I have left with? Plus X, added, mixing. Okay. Finally, this is my favorite one. What percent acid is water? 0. We should know that. We hope that that's true, right? We hope. So now, let's multiply. 20 times 0.24, that's 4.8. X times 0 is 0. And the sum of these two, 4.8 plus 0, should be equal to the product of the other two, 0.08 times 20 plus X. (1.6) plus 0.08x is equal to 4.8. 0.08x is equal to 3.2. You should recognize that 8 is going to divide 32, but let's make that 32. Let's slide the decimal point right 2 places on both of those, so we can do it by hand. 8x is equal to 320, and x is equal to 40. Before you commit that to your final answer, let's make sure that the answer actually makes sense. Look at the original problem. We had 20 liters of acid. We're adding 40 liters of water, and so it's diluting it down by a third. That makes sense. It's kind of in the right scale. So we can just say add 40 liters of water. It's a command, so technically it's a sentence. Implied you as a subject. Okay, last one. Same idea. We're just going to do this with grape juice so you don't get, all burned in your esophagus. We have a 10% grape juice. We're adding grape juice. So when I add that, what am I really adding? I'm going to put the word pure down. And we're going to make it 20%. The thing that I'm adding is the pure grape juice. That's sort of implied, but you got to read the problem carefully to kind of decipher that. we'll simplify this percent liters of solution, then liters of grape juice. I'm going to put everything down that we already know, 0.1, 0.2, 800 mils. Oh, let's not do liters, let's do milliliters. Change my units down. 800 of 10%, and X of the pure. Solution. SOLN is the abbrev for solution. Yep.
Wouldn't the pure, wouldn't it be 100% grape juice?
It will. We're going to write that down as a as like an extrapolation one. That's going to be 1. So yeah, not 100, but 1%. 100%. And then finally, the milliliters of solution of the 20% should be what? And then let's do some multiplication. 1 times x, and 800 times 0.1 would be 80. Vertically add 80 plus x. Horizontally multiply 0.2 times 800 plus x. These are problems you should be able to do without a calculator. You can do 0.2 times 800. 2 times 800 and then slide the decimal point. Then you get 0.8x equals 80, which you can then make be 8x equals 800. And we can say it takes 100 milliliters of pure grape juice.
So what's the x then? After you multiply the 0.2 and 2?
Oh, there should be an x right here.
Yeah.
Okay, last one. We'll set this up and get as far as we can go. 55% acid mixing with a 30% acid to make a 40% acid. The percents we've got down 0.55, 0.3, and 0.4. And we want to make 50 milliliters of the 40%. Everything else I'm going to extrapolate. This is the only information I can actually pull down onto the table. So let's try to extrapolate what we can. What do I put for the number of milliliters of the 55% acid? So X is fine. What do I put for the other one? 50 minus X. Doesn't matter which one of them the X is, just as long as the other one's the other one. That's all you have to do. Now everything else is just multiplication. 0.55X, 0.3 times 50 minus X. Add. And multiply. There's your equation. It got very, very far, and now it's glitching. It's okay, we'll let you solve it while I wait for this to catch up, if it ever does. Come on, yes you can. See, that now it like catches up with all the pen strokes I was making. Okay. I know. But you know what? I'm okay with that. Let's finish this. 0.3 times 50 is 15. Minus 0.3x equals 0.4 times 50 is what? 20? So you get 0.25x equals 5. Multiply both sides by 4. X is equal to 20. So just to be complete, it takes 20 milliliters of 55% acid and of 30% acid. Okay, one final point. You're going to have a problem on your homework. Talk about evaporating water instead of adding water. I'll leave you to think about what's going to happen to the volume and how evaporation is different. Just know that that's intentional. You can do it. Okay?